Welcome everyone to my talk Creating a Cloud-Native Serverless Web App, an AWS project reference. My name is Dennis Creutz and I'm a managing IT consultant and cloud architect for Prodyna SE in Düsseldorf, and I've got a strongly focus on the AWS cloud. The customer I want to talk about today is NOW, and they are coordinating funding programs in the field of sustainable mobility for the Federal Ministry of Transport and the Federal Ministry for the Environment. And they are located in Berlin, Germany. Our project goal was to create a system that makes it easy and intuitive to apply funding for e-charging stations. So this basically means when you're a company and you build some e-charging stations, then you can get some money back from the German government. Our solution was to create a multi-stage system in the AWS cloud that is completely cloud native, cost-effective, serverless, and can be easily deployed using infrastructure as code. Now I want to talk about the workflow behind this funding program, because you don't start at the portal we built, you start your application at the KfW. The KfW is a special German bank responsible for these funding programs. And there you enter your basic data, like your name and everything, and you get a reference ID. And with this reference ID, you can come to our portal, come to the NOW portal, and here you enter your charging station model and everything, all this important data for the funding program. And at the end of this step, you get a reporting ID. And with this reporting ID, you go back to the KfW. And then you finally get your money back. Here are some impressions of the front end we built. Here we worked closely together with our internal design department to create a front end that is very intuitive and very easy to use. But I think most of you come here for some more technical stuff. So this is the solution architecture for the AWS cloud, and I want to walk you through the important parts of this architecture. So let's start with the front end. The front end was built with React, TypeScript, and AWS Amplify. What is AWS Amplify? AWS Amplify are basically three parts. The first part is the service itself, and this is for the CICD pipeline and for hosting the front end. The second part is the front end library that is for connecting the front end with the AWS services, and you get some ready-to-use UI components. We will see that a little bit later. The last part is the Amplify CLI, and you can use the CLI to configure the Amplify service and the library. So it's basically the glue between all these parts. Here you can see an example of the AWS Amplify service in the AWS console. You can see here the build pipeline and the hosting. So we got three stages: dev, prod, and QA. And you can see here the pipelines for the deployment. This is one example for ready-to-use UI component you can get with Amplify. This is a login module, and we modify this to our use. And for authentication and authorization, we use Amazon Cognito. And Cognito is a simple and secure user sign-up, sign-in, and access control service. And it supports some basic standards like OpenID Connect and SAML. And it's very, very cheap because you don't pay anything when you're under 50,000 users. And like many other serverless services, it scales automatically. One important part or nice feature from Cognito is that you not only can get a token from your authentication service, so a JWT token, but you can get some temporary AWS credentials as well. How this works? So in the user pool where your users are, you can get your token, or your user can get the token, and then they can exchange this token for temporary AWS credentials in the identity pool, and then they can use this temporary AWS credentials to access other AWS services. So, for example, in our project, we use this in combination with AWS API Gateway and to restrict some paths. So, for example, our admin users were the only one allowed to access everything after /restricted. So no normal users could access this path. So we talked now about the front end, and I already mentioned a little bit about the API. For the API, we use Amazon API Gateway. And this is basically API as infrastructure. So you don't write your API in your Spring Boot container or something like this, but it's API as a service, as infrastructure. Got some nice features. It scales automatically, authorization and access control in combination with Cognito, for example. And it's very easy to call other AWS services from the API gateway. And in this project, we use the API gateway as a secure layer for our backend in combination with AWS Web Application Firewall to protect against the most common attack vectors. One more very cool feature from the API gateway is that you can export your whole API gateway definition as a open API or Swagger definition. So you got one file, and then the description of your whole API is in this file. And then our front-end guys could use this export together with an open API generator to generate a TypeScript library. And then it was very easy to call our API from our front end. So we talked about front end, we talked about API. The next step now would be to talk about our back end. And for our back end, we use AWS Lambda. And Lambda runs code without thinking about servers or clusters. So we can focus on writing code and don't need to think about how many CPUs we need, how many RAM and everything. So it's quite neat. And we got even more features. It scales automatically and it's automatically highly available. And it's got a very good integration with many AWS services, so it's pretty easy to call Lambda from other AWS services, and it's pretty easy to call other AWS services from Lambda. And it got a very generous free tier. So you basically get millions of executions for free every month. And so it's very, very good for smaller projects and POCs and stuff like this. And in our project, we use Lambda for all our backend tasks. So mostly for CRUD operations against the database, and we wrote our Lambda in Node.js. Now I want to talk about some pros and cons with our Lambda only backend. The pros are it was very, very cheap. So NOW basically didn't pay anything for the whole backend. It scales automatically because it's serverless. It was automatically highly available. And it basically was maintenance free. So we didn't need to care about software patches and stuff like this. The cons are the warm start versus cold start problematic. We needed to place our Lambda functions in a VPC, and this makes some problems. And the last point is not really a con, but it's something that's very interesting is that less RAM doesn't mean that it's cheaper. And now I want to talk about the three cons a little bit more into detail. Cold start versus warm start. Lambdas are containers behind the scenes. And first time when you call a Lambda function, this container will spin up. And this takes more time for the execution of the Lambda function. This is called a cold start. And each call after that is a warm start and much faster. So this is basically cold start versus warm start in a nutshell. Very simplified. It's a little bit more complicated than this, but let's keep it like this. And when you don't call your Lambda function for some time, then this container will shut down again. And the next time when you call your Lambda function, you got a cold start again. So, but how to prevent cold starts? There are basically two options to prevent cold starts. One unofficial way is to call your Lambda functions every X minutes to keep it warm. This will increase your cost slightly, not very much, but it's not supported by AWS, and you're not guaranteed that you only get warm starts. So, and because of this, there's an official way, reserved concurrency, where you can say, okay, I want to have X lambdas stay warm every time. And then you get guaranteed X lambdas warm every time. This is supported by AWS, but you need to pay for this. And it's not just a little bit, you need to pay for this. So these are the two ways how you can prevent cold starts. Then Lambdas and VPCs. Lambdas normally run outside of a VPC. A VPC is basically an isolated network part inside your AWS cloud. And but when you want to access private resources that are deployed in a VPC, your Lambda must be deployed into this VPC as well. And then what happens is that network devices are created in each necessary availability zone. So in a nutshell, this means that in each data center where you got resources, you need a network device to access these resources. There are some problems with this. The Lambda cold start is much slower in a VPC. And when you want to access services outside the VPC, your Lambda function need access to the internet, or you need to create a VPC endpoint, and this endpoint is not for free, it will increase your costs. And the last problem is that when you use infrastructure as code, like Terraform or CloudFormation, to deploy your Lambda functions, and then you want to destroy your Lambda functions, sometimes this will take very long. AWS already worked on this. It was much worse some years before, but it still happens sometimes that your Lambda function takes 10 minutes, 50 minutes, sometimes up to 40 minutes to destroy. And this is because of the network device that need to be destroyed. Okay, and then the last part is you pay your Lambda function for the execution time and for the RAM you used. So that means that it not necessarily the Lambda with the lowest RAM limit that is the cheapest, because when you halve your RAM but your Lambda takes 10 times more time to execute, then you pay more. And this was a problem in our project, because we initially had all our Lambdas configured with only 128 megabyte of RAM, and they were extremely slow. So we asked ourselves, okay, how we find the best ratio between cost and performance, because we want to tweak our Lambda functions. And the answer to this is Lambda power tuning. Lambda power tuning is a small tool someone from AWS wrote, and it basically executes your Lambdas many times with different configurations. So it executes the Lambda function with a RAM limit of 128, with 256, and so on and so on. And then you get a nice graph you see here on the right side. And in fact, this is a graph from one of our Lambda functions. And the red line is the execution time, and the blue line is the execution cost. And you can see here at the top left, where we execute the Lambda function with 128 megabyte of RAM, that the execution time is very, very high. And even the execution cost is very high. So this is the worst time and cost. And in fact, the best costs are 512 megabyte of RAM, and the best time is 1028 megabyte of RAM. But because we feed our front end with our Lambda functions, every millisecond we can get is good for us. So we set up all our Lambda functions with 1028 megabyte of RAM. We don't pay much more for this, but we get some better execution time. Okay, so we talked about front end, about the API, we talked about the back end. The last thing I want to talk about in this architecture is the database. And for this, we use Amazon RDS Aurora MySQL in the serverless variant. And Amazon Aurora is a managed relational database service, and it can deliver up to 5 times the throughput of a normal MySQL database. And you get nice features like automatically snapshot creation, data replication in 3 different data centers, and your storage can scale automatically. And because we use the serverless variant, we don't need to care so much about CPU and RAM, because it scales automatically, and this is quite neat. So we basically got this workflow, this data flow. The front end sends a HTTP request against the Amazon API gateway, and the gateway sends the HTTP data to our Lambda function, to our backend, and the Lambda functions then execute the CRUD operations against our Aurora. So what you can see here is the only part that is not fully serverless in our architecture. The Aurora is serverless, but what you can see in the green part, in the public subnets, is a bastion host. And you can use a bastion host as you can think of a bastion host as a very, very secure virtual machine that only allows SSH access. And with this, the data analytics team and the developers can access the Amazon Aurora database from the public internet, because the database itself is placed completely private, so you can't access this normally. But this bastion host is, it runs all the time, and when no one uses it, it still creates cost, not much. But yeah, this is the only part that's not fully serverless. I want to talk a little bit about some database architecture improvements. We needed to use a relational database. And because of this, we needed to use Amazon RDS, Aurora. But when you're a little bit more free, you could use something like Amazon DynamoDB. And DynamoDB is a NoSQL database, and it's truly AWS Cloud Native, and it's very fast, and it's got a better integration with other AWS services. And what I mean with this is that the CRUD operations can be called directly over the AWS API, and because of this, you can call the DynamoDB directly over the Amazon API gateway, and you don't even need a Lambda function for this. So when you keep this in mind, this architecture could be very simplified to this, because we can call the database directly from the API gateway, and we don't need Lambda functions for this, and we don't need to place the DynamoDB inside of a VPC, and then we don't need a bastion host, and this would be much faster and much cheaper. In fact, the Aurora is responsible for about half of the infrastructure costs in this architecture, and with this it would be much cheaper. Okay, so and the last part what I want to talk about is our infrastructure setup. We use infrastructure as code, Terraform with Terra Grunt. 3 stages: develop, QA, and prod. So what is Terra Grunt? Because I think most of you already know Terraform, but what is Terra Grunt? Terra Grunt is a wrapper around Terraform, and the features we most used were that you can use Terraform code across environments, so across prod, QA, and dev. You can use common Terraform code. You can extract your backend and provider configuration, so you don't need to write in every module, in every directory, the same backend configuration, the same provider configuration. So this is quite neat. And the last feature we commonly used were all commands where you can execute Terraform commands on multiple directories, on multiple modules with just one Terra Grunt command. And this is quite neat for CICD pipelines especially. And yeah, let's talk about CICD. CICD, for CICD we use AWS services. We used AWS Code Commit for our JIT. We use Code Build as a build servers for Terraform. Code Pipeline as orchestration for the build pipelines. And I already said that AWS Amplify as a front-end build server and hosting. The problem here is that the AWS CI/CD services are not really good. There are lack of many features, and there are not many innovations. So before this project, I used this AWS services, I think 3 years before, and I was very shocked when I see that not much changed, and basically the same like 2-3 years before. And yeah, that's pretty bad. And they're sometimes very cumbersome to use. So now you ask why we used this CI/CD service from Amazon when they're bad. Because in this special project, we're okay. Because NOW didn't got a huge own internal IT, and they don't got any CI/CD infrastructure at that time. And so they only need the CI/CD infrastructure for this project. And it didn't make any sense to build a GitLab for this, because then you need to run GitLab on a virtual machine or in a Kubernetes cluster, and it's the whole architecture is serverless, but then the CI/CD pipeline will not be serverless. So it didn't make any sense. And the huge plus point of the AWS CI/CD services is that it's pay as you go. So we only pay for the JIT we used. We only pay for the build time we used and everything. So in this project, the AWS CI/CD services were okay. So we use them. Here you can see code pipeline, so the orchestration tool, and our pipeline were pretty basic. So the first job just downloads everything from code commit, the source code. The second job is the Terraform plan, and then the third job is the Terraform apply. So in our develop pipeline, everything gets deployed automatically. When you commit something, everything gets deployed automatically. In QA and prod, we don't want to have that. Here we want to have a human that can look on the Terraform plan on the output and can say, okay, that's look good, we can deploy this. So we added an additional approve step between the Terraform plan and the Terraform apply. Okay, so that's basically it. When you want to know more about this project and serverless architecture and everything, we wrote a whole success story about this. You can just scan this QR code to download the success story, and then you can read more about this. Or when you want, you can always contact me directly. Okay, so this was my talk. Thank you and have a nice day.